Moving on to section 25.4, we're going to discuss the structure of peptides. And remember, when we talk about a peptide bond, it's nothing more than an amide bond, but it's between amino acids. Okay, so we spent a lot of time talking about amino acids. We saw how they have a carboxyl group and how they also have an amino group. And so if you react the carboxyl group of one amino acid, so let's say you have something like this, okay, and then let's say we put another one next to it, okay, and we do something, and we're going to look at this in more detail in just a second. So let's say you have two different amino acids, and then you mix them up, okay, well, what's going to happen is that they can combine so that you lose water, so you lose two hydrogens and one oxygen, and then you form a bond between the two of them, so you end up with something that looks like this. So I'll try to sketch it out here without messing it up. So we have the carbonyl from the one in red, and then we have the nitrogen and one of the hydrogens from the one in blue, and then we have our carboxyl group like this. So the bond, the actual peptide bond, is the amide bond between the two. So that would be a peptide bond where I have that little squiggle line drawn to. And you're going to see this in more detail in just a second. But you see this molecule down here at the bottom of the page? This is called glutathione, and it says it's just an example of a tripeptide. And a tripeptide means there's three amino acids joined together. You can see they are glutamic acid, cysteine, and or cysteine rather, and glycine. So we see those put together. But the thing is that, yeah, we do have three unique amino acids. So we could write this in a condensed form by saying glutamic acid, then cysteine, and then glycine like this. Or if you wanted to use the one-letter abbreviation, if you really get fancy, you could say ECG. But it's not just enough to have these put together. They have to be assembled in the correct order. Like let's say, and you don't have to write this down, but let's say you assembled them CEG, right? If you rearrange them, would it be the same compound? No, it would not be glutathione. It would be something completely different. So not only do we have to put the amino acids together, but they have to be put together in the correct order in order to make a very specific peptide or protein or enzyme. And so let's say you want to make a dipeptide, okay? Dipeptide, just two amino acids put together. The simplest amino acid there is, and I'm not being facetious, is glycine, because the R group is a hydrogen, right? There's a hydrogen here and a hydrogen here, so there's no chiral center in it. And then I'd say the second simplest would be alanine, because its R group is just a methyl group. Well, let's say you put these two molecules, alanine and glycine, in a flask, and you tried to make them form a peptide bond. Well, there's two possible ways that the two peptides could, or the two amino acids could come together. I could get the carboxyl group of alanine and the amino group of glycine to come together to make this compound here. This compound would actually have a name. You'd call it alanyl glycine, but don't worry about that. We'll just call it ALAGLY. Just use the abbreviation. Or you could have the carboxyl group of glycine react with the amino group of alanine, then you'd have glycosalanine. But either way, you see that these are two different molecules. So these are different, okay? And so what if we wanted to just make one specific compound? How would we do that? Well, we're going to see that in a little bit. But before we get into that, we're going to get into some more background. And you might have noticed that both of those dipeptides on the previous slide, they were written in the same order. And then I had a nitrogen on the far left of the molecule, and the carboxyl group, or a carboxyl group, is on the far right. And that is a convention, okay? The convention, which means it's conventional, which means everybody does it this way, is that when we write peptides, we put what's called the N-terminus, or the amino group, on the left-hand side of our peptide, and the C-terminus, where we find our carboxyl group, we put that on the right-hand side. And again, this is a convention that's used all across the scientific community. So you see this peptide here, you would call this a pentapeptide, right? It has 1, 2, 3, 4, 5 different amino acids together. It's got a total of what? 1, 2, 3, 4 peptide bonds total in there. But anyhow, you see on the far left, we have the nitrogen, an alpha nitrogen here from our first amino acid. That's called the N-terminus. Sometimes you'll hear it called the N-terminal, okay? And that's totally fine as well. Same thing with the carbon. We call it the C terminus, but if you hear it called the C terminal, there's nothing wrong with that. Sometimes you'll see that kicking around. So the three-letter abbreviations can also be used. So let's say somebody wrote the structure of this peptide here. You've got alanine, glycine, cysteine, tryptophan, so on and so forth. Well, it is taken for granted that it is written with the N terminus on the left-hand side and the C terminus on the right-hand side. So again, it's a convention that we follow as chemists. Now, something else that I want you to remember, and this goes way, 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 way back in terms of your studying organic chemistry. If you go back to chapter 1, I think, of Organic Chemistry 1, we talked about hybridization. Remember that? We did a whole section where we talked about sp3 hybridization, sp2, sp, and we said, okay, well, what's the hybridization of this carbon right of this nitrogen right here, if I highlight it in blue, okay? If you look at it the way it's written, right, you see you've got the nitrogen, it's got a lone pair, it's got a bond to a carbon, it's got a bond to a hydrogen, and a bond to a hydrogen. I'll just put the carbonyl up here like this. And you might be tempted to look at that and say, that's sp3, okay? Because it's got 3 regions of electron density. It's got a lone pair, it's got 3 sigma bonds. That means a steric number of 4, therefore it's sp3. Wrong, okay? That's a big no-no. That nitrogen is not sp3. Why is it not sp3? It's because this lone pair, this little lone pair right here, is participating in resonance. You can see it here, and you see in the 3rd resonance form that there's actually some double bond character to that bond. And if you look at this structure here, I mean, if I just redraw it, we'll say here we have our oxygen with our negative charge, and we have our double bond, and we have, right? So now if you look at the nitrogen, it's got a steric number of 3, and so you might think its hybridization is sp2, and in fact, it is sp2. So I'll use the Drake meme and put a big check mark by that. So it is actually sp2, and the only way it can be sp2, or the reason it is sp2, I should say, is because this lone pair is participating in resonance. Okay, so that means it has to be in a p orbital. So there you have it. Now, since there is, so if you're like, well, why are you rambling on about this stuff from chapter 1? Okay, what's the big deal? The big deal is this, is that the carbon-nitrogen bond in a peptide does have some double bond character. You see it right there. If you look at the resonance hybrid, one of them has a double bond there. So it has some or partial double bond character. And so what's the consequence of that? The consequence of that is restricted rotation. Right? If I just showed you this structure, you'd say, oh, well, this bond can rotate like nothing. It just spins around and around. But then if you look at the full picture, you look at this, that cannot rotate. And so it means, since there's partial double bond character there, it means the barrier of rotation between the S-cis and the S-trans is really high. It's 80 kilojoules per mole. So it's a pretty high barrier to rotation. And that's one of the reasons why amides have this backbone that's tend to be locked in certain conformations here, because the peptide is going to prefer the S-trans conformation. You can see why. There's less steric hindrance here. So if you're wondering what S-cis and S-trans stand for, the S stands for sigma. So it stands for sigma trans, right? Because if you look at this structure, it looks like a sigma bond, but we know it has some partial double bond character. And it's the same thing here. This would be sigma cis. So it's put more eloquently maybe here on this slide. It says peptide bonds of the peptide backbone have a preference for the S-trans conformation. So that's why it's always written in this, up, down, or zigzag pattern like that when we write our peptides out. And we're going to get some practice on that. It says the other backbone bonds, right? The ones that are highlighted in green, these experience restricted rotation. But all of the other ones, like this one, okay, or this one, etc., those all experience free rotation. And so it allows the peptide to adopt a variety of conformations. And that's very important when you start looking at things like an alpha helix or a beta pleated sheet. And we're not going to cover those in this class, but if you haven't discussed those things in your biology classes already, they will be covered in more detail in biochem. Okay, so you will see those concepts, and they are mentioned at the back or towards the end of this chapter. Well, another thing, if you've ever permed your hair before, if you know anybody who's into getting their hair permed, they might know a little thing about disulfide bridges. Okay, so it says the formation of disulfide bridges is critical to the structure and function of many proteins. And we'll put here and perms. Okay, if you want to get your hair permed. Okay, it takes advantage. I'm not joking, of the thiols in the amino acid residues in your hair. So here we have cysteine. So this is cysteine, okay? And this is a cysteine here, okay? Now, we have two cysteines, and what happens is they come together in an oxidation reaction where we form a disulfide bridge, right? So you guys know that this is called a disulfide, this thing here. Well, when you form this actual molecule here, this has a name, it's called cysteine. So cysteine, like that. Okay, so cysteine. And again, not to go into all the detail, I'm going to leave the perm thing as an FYI. I'll put that here as an FYI if you want to go on YouTube and you could Google or search disulfide bridges or chemistry of perms or something. But the idea is this, is that we all have cysteine residues in our hair. And then what they do is we also have disulfide bridges in our hairs. So they reduce it, okay, to open up all these to leave all the thiols free. Then they wrap it around a curler. Okay, so they wrap it around a curler, and then they oxidize it to form all the disulfide bridges. So the disulfide bridges are what holds the curls in place in your hair. Now, if you're like, well, why doesn't the perm stay? Well, eventually they break, right? They're brittle, so they're going to fall apart, and your hair is going to go back to its natural state. But anyhow, I'll leave the perm thing as an FYI. Maybe next semester I should put something in, maybe a video about perming your hair or something. Anyhow, another little bit about these disulfide bonds. Okay, so it wasn't just to talk about perms, okay? It says here that in some proteins you have disulfide bridges. So it means they have more of a biological significance than they do a fashionable significance, okay? So if you take a look at these two peptides here, you see that both of them have disulfide bridges, right? You see one here. This is in this, right? We have one long strand or one long chain of amino acids all linked together. And then you see that you made this turn here, this like kind of hairpin turn. Well, that's put together by this disulfide bridge, and that's called an intra-strand disulfide bridge. Whereas if you had two separate amino acid chains and then you link them together somehow, this is called an interstrand disulfide bridge. So you should know the difference between an intrastrand disulfide bridge and an interstrand disulfide bridge, which isn't that difficult to remember. Now, biologically relevant peptides, I don't make my students memorize these really. I just think you should understand that the significance of how just one change, one amino acid residue is changed, and then we completely change the function of a peptide. Okay, so we have two enkephalins here on the top, and don't worry about the long names or anything. The one on the left is leucine enkephalin, this compound here, and the other one here, this is methionine enkephalin. If you look at the first four residues, starting on the N terminus, you have tyrosine, glycine, glycine, phenylalanine, and you have the same four here. The only difference between them is they're two amino acids at their C terminus. For leucine enkephalin, it's a leucine, and for methionine enkephalin, it's a methionine, but they have very different functions, these two compounds here, okay? They both function in the control of pain in the brain, but you see how they just differ in one residue here. I thought that was one of my kids. That's the wind knocking the door. Anyhow, bradykinin says here is a hormone that dilates blood vessels and acts as an anti-inflammatory. You see all the amino acids linked together there. Of course, we always write it with the N terminus on the left-hand side, and then we put the C terminus. The C terminus is always on the right-hand side, and again, that's the convention. What else? Here's a good example, I think, that what I was getting at, where you have two compounds that are pretty similar, but small changes have big differences in biological function. So on here we have vasopressin and oxytocin, and you can see that it's got an intrastrand disulfide bridge. That's pretty cool in both of them. And you see that all the amino acids are the same in the residues, except for this phenylalanine and isoleucine and then arginine and leucine here. This is the only difference. And look at the difference in their function. Vasopressin has to do with reabsorption of water by the kidneys, whereas oxytocin induces labor and allows the mother to nurse. Anyhow, and another thing that I'll just mention here is you see how they stuck this, right? You always think of, or based off of what I taught you, you would think of the C terminus as ending like this with the carboxyl group. Well, you notice that they put NH2 here. So that means that the hydroxyl group has been replaced with an NH2 group. So it's not a carboxyl group. It's actually a primary amide at the end in the compound. All right. So what they're asking us for here is to draw the structure of the following peptide. So watch carefully. I'll show you how to do it, and then you'll never make a mistake, okay? So if you look at your handout of amino acids, since all the wedges are drawn in the same orientation for the naturally occurring or L amino acids, what I'm going to show you is this, okay? I need you to remember this. When you're drawing a peptide, you always want to remember NCC, okay? You're just going to do NCC, NCC, NCC for every amino acid. So here we have 1, 2, 3 total amino acids. So what does that mean? It means we're going to go like this. We're going to have nitrogen, carbon, carbonyl. So NCC. Nitrogen, carbon, carbon, carbonyl. NCC, right? NC, maybe I should call it NC carbonyl. Then N, then C, then carbonyl. You notice that some of my carbonyls are up and some of them are down, okay? So now what I'm going to do is for my N terminus, I'm going to convert it into an amine. For my C terminus, I'm going to convert it into a carboxylic acid, okay? So now we just have to fill in the R groups. There's a total of 1, 2, 3 R groups, right? There's 3 methylenes here that we need to populate with the R groups. So for an isoleucine, our R group is going to be an isobutyl group. Now, if it's pointing down, you're going to make it as a dash. So we're going to have a dash going down like this. There's my isobutyl group. For my alanine, my R group is going to be pointing up, so I'm going to make it a wedge. I'm going to make it a wedge like this. And then for my glycine, well, there's no chiral center there, so there's nothing to worry about down or up there. Now you can see there's 2 things that are missing from my peptide, and that is the hydrogen on my nitrogen of my amide like that. Now there's nothing wrong with the way I've drawn it like this, but I like to draw it like it's at physiological pH. So I like to draw it as the Zwitter ion, where I have the cation here and the anion over here. Now there's nothing wrong with the way I did it, okay? But you guys have been studying organic chemistry long enough to know that it would be okay if I went N up C, right? NC carbonyl, right? NC carbonyl, NC carbonyl. There's nothing wrong with writing it that way. So now I'm going to finish my N terminus. I'm going to finish my C terminus. Now all we do is this, is if the R group is pointing up for my isoleucine, or sorry, for my leucine, I'm just going to change it to a wedge. And there you have it. Put my nitrogen here. For my alanine, the R group is pointing down, so I make it a dash. Done. Put a hydrogen in here, and there you go. So either of these, okay, either of these is fine. So for side chains or R groups, okay, here's what we're going to do. If it's pointing up, we'll say it's a wedge. And if it's pointing down, we'll say it's a dash. And that's it. Okay, that's how you're going to draw a peptide in this class. So make sure you try the practice problems that I asked you to do, where it says drawing a peptide, because it's going to, there might be a couple of those on the homework. Now, let's say I gave you a compound like this. Okay, you can see that this is a pentapeptide because it goes NC carbonyl, right? Then it goes NC carbonyl. There's 2. Then it goes NC carbonyl. There's 3. Then it goes NC carbonyl. There's 4. And I'll see if I can find some purple here. And it goes NC carbonyl. There you go. There's 5. So this is a pentapeptide. Now it says use 3-letter and 1-letter abbreviations. Now remember, you don't have to memorize all the amino acids in this class. If we take a look at the first one, it's got an isobutyl group. So that is a leucine. Let me go back to my black pen. So this is a leucine. Then here we have a methyl group. And so that's an alanine. Here we have a methyl group, right? This is CH. It's not CH3, it's CH2, but you replaced one of the hydrogens with a phenyl. So this is phenylalanine, which is PHE. The next one is cysteine. So cysteine, in case you didn't pick up on it, was CYS. And the next one, it's not glutamic acid, it's aspartic acid. So that's it's ASP. ASP. Okay, so those are the three-letter abbreviations. We can put them together like this. If you're really fancy, you can put the spheres together or the circles together like this and say LEUALAPHE and aspartic acid, right? That's totally fine to do it that way. But if you really want to be, fancy, then you could just use the one-letter abbreviation, which would be LAF for phenylalanine, which is kind of funny, C for cysteine, and then aspartic acid is D. Okay, it's kind of a weird one there, but there you go. So we have leucine, alanine, phenylalanine, cysteine, and aspartic acid are the 5 amino acids. And you notice that the R groups, right? This one's pointing up, so it's on a wedge. This one's going down, it's on a dash. This one's pointing up, it's on a wedge. This one's down, it's on a dash. This one's up, it's on a wedge. Cool? So there you go. Just remember your NCC, and you're good to go with your peptides. Okay, let's take a little break before we get into sequencing a peptide, which is determining the structure of a peptide. Okay, if you go back to something like, I don't know, even this peptide here, if you're wondering, like, well, how does somebody determine the structure of this? I mean, the NMR would be just so complicated. In the mass spec, I mean, you'd have a huge numbers, and there's so many amides and carbonyls and hydroxyl. I mean, how do you get any information about that? Well, what we do is we pluck off the amino acids, right? We pluck off this one, then this one, then this one. We pluck them off one by one. And as we take them off one by one, kind of like picking the flowers off of a petal, right? Petals off of a flower. We analyze them one by one, if that makes any sense. And so, phone call from my dad. So what we're going to do is we are going to, where are my students at? There we go. What we'll do, well, I guess I'll stop recording in a second.